In the previous lecture, we learned about how atoms can be turned into ions and how that those ions can form chemical bonds through their mutual attraction, the so-called ionic bond, which causes those atoms to form into molecules. In this lecture, we're going to learn about some additional ways in which atoms can bond together into molecules. Our next example of a chemical bond is what's called a covalent bond. And in covalent bond, what happens is two different atoms end up sharing some of their valence electrons. So let's see how and why this can happen. Consider two fluorine atoms. Here I have a fluorine atom there, here I have a fluorine atom there, and I bring them close together. Now when you look at an individual fluorine atom, we can see that there's two electrons in its innermost shell, so that's filled, and then there's 1, 2, 3, 4, 5, 6, 7 electrons in its outermost valence shell. Remember, atoms want to have their valence shells completely filled. And so if it could have another electron right here, this atom would be completely happy. Now, its neighbor over here has this guy, and he really wants to have his shell filled too. And so I've got this single electron here that's unpaired, and this single electron here that's unpaired. What happens is these two electrons get shared by these two atoms. And so you can see in the next slide that the atoms have essentially bonded together, and these two extra electrons are acting as a shared pair for both atoms. And that creates an attraction that bonds these two atoms together. So you have two individual fluorine atoms which bond together into the fluorine molecule F2. The key thing here, though, is that these outermost valence electrons are being shared between both of these atoms. That's what makes it a covalent bond. In the previous example of an ionic bond, we actually had electrons completely removed from one atom and electrons completely added to another atom. Here, it's slightly different because the electrons aren't being taken from one and given to the other. They're being shared at the same time. And so this is what makes a covalent bond. So a covalent bond is a bond that occurs where you have an electrical attraction in which atoms are held together by their mutual attraction for shared electrons. They both want to share those outer electrons to make their shells filled. And so that's what forms the bond. There are two electrons within a single covalent bond, and the covalent bond is usually represented by a straight line. So here we see the kind of schematic representation that we saw last time with the dots representing the electrons. And here you can see that these two dots here, they're effectively shared by these two fluorine atoms. Now, another way that chemists will sometimes draw this is they'll draw it with this, where this horizontal line represents the shared electrons. And so that single line represents the shared electrons that make up the covalent bond. This is a single covalent bond. The other dots are understood, so we know the other electrons are around. But this is how we represent a covalent bond. Now, one of the things that's really important to know is that the number of covalent bonds that an atom can form equals the number of unpaired valence electrons. So unpaired valence electrons are what enable covalent bonds to form. So let's look at an example. The familiar example of water, H2O. If we look at the oxygen atom right here, we can see that in its valence shell, it's got two paired electrons here, two paired electrons there, and we have two unpaired electrons, one here and one there. So that means that oxygen has the possibility of forming two different covalent bonds. Now we know hydrogen has only one electron, and so it has its own unpaired electron. So here we have two hydrogens, each with their own unpaired electron. Now what happens when this electron gets paired to that electron in a covalent bond? Well, that adds an extra electron to the oxygen shell, which brings its total up to 7. It needs one more to be complete. Remember, it's trying to get to 8. So when this guy bonds over here, the electrons being shared by the oxygen plus the electrons that oxygen already has gives you 8. And we can see that over on the right here 1, 2, 3, 4. The two that are shared make 5, 6. These two that are shared make 7, 8. So the oxygen now has its shell completely filled. And the same for the hydrogen. The hydrogen originally had 1. Remember, the very first shell, the one that hydrogen uses, can only hold 2. So when the hydrogen shares 1 with the oxygen, it now has 2 in its valence shell. This guy has 2 in its valence shell. So all of these atoms have their valence shells completely filled by having this process of sharing the electrons. That's pretty cool, right? That's how hydrogen bonds to oxygen. And that's why you get H2O instead of H6O. It's because there are only 2 unpaired electrons in oxygen available for forming bonds. Here we see another example, ammonia, which has the chemical formula NH3. So that's 1 nitrogen atom plus 3 hydrogen atoms. If we look at nitrogen, its outermost valence shell has 2 electrons that are paired together and 3 that are unpaired. So that means that nitrogen is able to have 3 bonds form. And so this electron of this hydrogen atom gets shared here, this one gets shared there, this one gets shared there. We have these covalent bonds, and again, now all the hydrogens have 2, so they're filled, and the nitrogen now has 8. So by bonding 3 hydrogens to the nitrogen's valence shell becomes filled with 8, and that's what it wants to be most happy. Okay, here's another example. We have carbon, which has 4 unpaired electrons. So carbon can actually make 4 different covalent bonds, and so when it bonds with hydrogen, it can make CH4, which is also known as methane. Again, we see that same process. Carbon has 4, so it needs 4 additional electrons to bring its total to 8 to completely fill up that valence shell. I've got 4 hydrogen atoms, each with 1 free electron, so when those 4 hydrogen atoms bond to the carbon, you get each hydrogen gets 2, so they're all full, and the carbon gets 8, so it's full, and that is a happy molecule. Now, continuing our discussion of covalent bonds, we've already seen the number of covalent bonds an atom can form equals the number of unpaired valence electrons. Now here's something that's new. Multiple covalent bonds are possible. Let's consider oxygen. Now, oxygen can bond to itself and form an O2 molecule. So 2 oxygen atoms bond together and form an O2 molecule. And that is done through the process of covalent bonding. Now, oxygen has, if I look at this particular oxygen atom on the left here, it's got 2 electrons that are paired together, 2 electrons that are paired together, and 2 electrons that are not paired together. And so each atom of oxygen has 2 unpaired electrons that are available for bonding. And when these 2 oxygen atoms get close together, those 2 sets of electrons can pair up and form what's called a double covalent bond. And so these 2 guys are sharing and these 2 guys are sharing. Now, the shells are not filled up all the way to 8, but the fact that these 2 guys are both equally forming bonds makes for a stronger bond. And so oxygen forms O2, which is made by a double covalent bond. We see the same sort of thing with carbon dioxide. Carbon dioxide is, of course, a very famous gas these days because of its role in the greenhouse effect and global warming. But here we have a carbon atom which is forming double covalent bonds with 2 oxygen atoms. And so here we see that there's 2 sets of electrons on this side that are forming a double covalent bond. There's 2 sets on the right side that are forming a double covalent bond, and that makes carbon dioxide. And so each of these bonds is, so each line here represents a pair of electrons that are being shared. So on the right side, there's 2 pairs of electrons being shared, and on the left side, there's 2 pairs of electrons being shared. If we look at nitrogen, which actually forms a triple covalent bond, we can see that here I have 2 nitrogen atoms that are bonded together, and there's three sets of electrons, three electron pairs that are being shared and forming a triple covalent bond. And you can see these three lines here. Again, each line represents two electrons that are being shared, and so there's a total of 6 electrons being shared among 3 covalent bonds. The next topic we want to discuss is what are called polar covalent bonds. And basically there's two different situations that we'll encounter with this. We're going to talk about what happens when the atoms are of the same species. In other words, here I've got two hydrogen atoms that have formed a covalent bond, and so these two electrons are being shared among both of the atoms. Now, because hydrogen is identical to hydrogen, these two electrons are basically going to be shared evenly. And you can see this in this figure over on the right, which might look a little bit confusing, but it's actually basically a simple idea. What this image is showing is the probability that an electron will be at a particular location. In other words, it's saying that the electron's more likely to be in the middle than it is to be off to the sides. Remember, the electrons aren't just staying stationary. They're zipping around these hydrogen atoms in different ways. They're jumping around. And one way to think of this picture is to imagine that you are taking a photograph every 10th of a second, or even every millionth of a second, however quickly you're doing it, and you superimposed all of those images. And so each photograph was showed you where the electron. So the first picture of the electron was right there, the second picture of the electron was right there, the third picture of the electron was right there. You take many, many, many pictures, and what you're going to find is that the electron tends to spend most of its time in the middle between the two atoms where that bond is, but occasionally it'll be on one side or the other. But that sharing of the bond really shows up, that sharing of the electron in that bond really shows up in the middle where the electrons are spending most of their time together. Now, because the hydrogen in the hydrogen here are the same, the electron is going to spend about as much time on this side as it does on that side. It's going to spend more time in the middle, but you can see there's like a symmetry. This almost looks like a peanut shape, but really the key thing is that, it's kind of the same on the left as it is on the right. That symmetry is because both hydrogens are identical. Now, here's the other kind of situation where the sharing is not symmetric. Here we have hydrogen bonding with fluorine, and when we look at the probability diagram, we can see, again, the electron spending most of its time between the two atoms, between the hydrogen and the fluorine, but it's spending some time around the hydrogen and some time around the fluorine. And what we see, the fluorine actually has a stronger pull on that electron, and so the electron spends more time around the fluorine than it does around the hydrogen. And we can see it can actually be a little bit further away from the fluorine than it is from the hydrogen as well. So this is just kind of showing you, again, the probability that the electron is going to be in a particular part of space surrounding the atom. And we see most of the time the electron spending time where that bond is, but occasionally it's flipping back and forth into other places. Still, the main idea here is that in this situation, because the fluorine has a stronger pull on the electron than the hydrogen, it's not a symmetric picture. So the electron is going to spend a little bit more time over here than it does over there. And what that means is that this side of the atom is going to be a little bit more negative than that side of the atom. Because the electron's spending more time over here, this guy's effectively going to be negative more often than it's not negative on the right side. Or I should say on the fluorine side, because this could easily be upside down, right? But on the side where the fluorine is, the electron is going to spend more time, and that's going to make this side of the atom a little bit more negative. Now, in the previous slide, I talked about how the fluorine had kind of a stronger pull on the electrons than the hydrogen did. The amount of pull that a nucleus has on an electron, that principle is called electronegativity. And it's the ability of a bonded atom to pull on a shared electron. Greater electronegativity means greater pulling power. In other words, an atom that has more electronegativity is going to pull the electron to its side more often than the other atom will be able to. And by the way, this is another pattern that shows up in that periodic table. Isn't it amazing how many different things a periodic table can tell you about the different elements? Well, one of the things that it can tell you is the electronegativity of a particular atom. Now, you can actually look up the value for the electronegativity for a particular atom, but as a good rule of thumb, the electronegativity increases as you go along the periodic table in an upward diagonal fashion. So the atoms over here tend to have a very low electronegativity. They're not pulling very strongly on those shared electrons. But up here, the electronegativity is higher. In the upper right corner, the electronegativity is higher. So atoms in that part of the periodic table will have a much stronger pull on shared electrons. Okay, in this slide, we're going to be looking at another kind of notation. We can see this blue arrow here, and there's one for that one here. And the little blue arrow has a little plus sign at one end and the arrow going away from the positive. And this is showing you the direction in which the atom tends to be more negative. Now, sodium fluoride, we've talked about, has an ionic bond. Do you remember what an ionic bond is? That's the kind where actually one atom completely gains an electron and one atom completely loses an electron. So the sodium becomes positive and the fluorine becomes negative, and this represents the biggest amount of charge difference. So in other words, this side is going to be way more negative than that side. Now, that's an ionic bond. Over here, we have hydrogen fluorine, which forms a polar covalent bond. So instead of the electrons being swapped, they're being more shared. And so the electron spends not all of its time or most of its time over here necessarily, but it spends a lot more time over here than it does over there. And so it's going to tend to be a little bit more negative on this side than on that side. And so again, we see this arrow showing the direction, so this is telling me that the hydrogen side is going to be a little bit more positive and the fluorine side is going to be a little bit more negative. Now notice the length of the arrow. This one is shorter than that one. That's because that charge discrepancy is smaller here. Now if we look at the third example, molecular fluorine, that's two fluorine atoms bonded together, they form a nonpolar covalent bond. Nonpolar means that the electrons are not stretched out to one side or the other. So here we have polar. The electrons have that asymmetry where it's more negative on one side than the other. But when you have an atom bond to itself, you have that symmetry. So the electron spends just as much time over here as it spends over there. So this atom does not tend to be more positive on one side or more negative on one side than the other. It's symmetric, and so we call that a nonpolar covalent bond. A polar covalent bond, that's the kind where the electron spends a little bit more time on one side than the other, and it makes that molecule a little bit more negative on one side and a little bit more positive on the other side. It's positive over here because the electron's spending less time over there. That should, I probably should have said that before, but hopefully that's obvious that if it's more negative over here because the electron's spending time over here, the electron's spending less time over here, leaving this guy more positive. And so here we have sodium fluoride, which is an ionic bond, where the electron's actually been moved over to here. We've got one electron extra on this side and one electron less on that side. Now we want to look at another kind of bonding, which is called metallic bonding. The things that people normally think of as metals, like gold and copper and aluminum, those are the kinds of atoms that engage in metallic bonding. And I have it written here that metallic bonding is like covalent bonding on steroids. Now, with a covalent bond, you have two atoms that are sharing an electron, or sharing multiple electrons. But with metallic bonding, all the atoms are sharing all the unpaired valence electrons. In other words, rather than having this atom and that atom sharing an electron, They're all sharing the same electrons. What that means is that this electron can migrate anywhere in this region from one atom to another. That's why things like copper and aluminum and gold are such good conductors of electricity. So these different metals that are such good conductors of electricity, the reason that they're such good conductors of electricity is that their electrons in their outermost valence shell, they can move to any atom they want. And so currents are made up of moving electrons. These electrons are able to move down these materials very, very easily. So here's sort of a review of some of the features of metallic bonds. The outer electrons in metal atoms are held only weakly by the nucleus. That's why they're free to move from one atom to the next. This weak attraction allows them electrons to move quite freely. This mobility of electrons accounts for many metallic properties, such as the fact that they're good conductors of electricity. By the way, it's also part of the reason why metals are such good conductors of heat as well. One other thing that we can mention about metallic bonding is that it can be used to bond multiple types of metals together. And a mixture of different types of metals is called an alloy. By mixing different amounts of the different metals of the alloy together, you can get different properties, different conductivities of electricity, different colors, etc. Here we see an image of the Sacagawea dollar coin, which consists of a copper core covered in an alloy of copper and zinc and manganese, which were combined in just the right proportions to give it that characteristic golden color. And so by mixing different metals, you can change the properties of the resulting chemical alloy. So you could change the color, as I mentioned, you could change the conductivity of the material. Different properties can be changed by having different proportions of the constituent metals. But when you combine these metals together, their bonding is the same as with the pure metals. It makes use of that metallic bonding. And that's just about it for this lecture. We're going to have one more lecture on this chapter, which will further investigate the means by which the forces between atoms and molecules come to play.